Welcome to the Festival of Dangerous Ideas podcast. Our 10th festival, like thousands of other events, was no longer able to proceed due to the rapidly evolving situation around COVID-19. While our 10th anniversary is postponed, we have 9 years of stimulating dangerous ideas in the archive to ponder, reminding us of the eerily relevant conversations that take place at the festival each year. We've used water unthinkingly for the entire of human civilization, and mostly until now we seem to have gotten away with it. We're now racing dangerously to the end of our water-rich era, concludes Alok Jha at the end of his 2016 talk. In this session, author and journalist Alok Jha discusses how our modern world is trying to deal with obtaining more water than we have access to. From our agricultural and civilizations rapidly developing to worldwide conflict, will we eventually run out of water? Please enjoy Alok Jha with his session, Waterwall.
Thank you all for coming this afternoon. It's a real pleasure to be here in Sydney. It's the first time I've spoken here, so forgive me if I get a bit nervous or excited. It's a real pleasure to be in this place. I'm going to speak for half an hour, and then hopefully I'll be able to answer your questions as well about this substance, which I find fascinating, and I'm hoping that by the end of this session you'll find fascinating as well. Water is something that every one of you has interacted with many, many, many times today. Whether you've had a shower, you're drinking a cup of tea, you're drinking water here before you came into here, eating food, whatever. You've interacted with it multiple times. But I bet you don't really even think about it very much at all. So I want to make you think about it, and I want to make you think about how this world is trying to deal with the fact that we all need much more of it than perhaps we have as easy access to. So let's just look at the Earth, first of all. I mean, if you looked at the Earth from space, if you're an alien, you'd think this is a water planet. The little bits of land, the dry land, they're kind of irrelevant almost. The water on the surface of the Earth is the most important thing. 70% of our surface is covered in it. Life started in the oceans. It thrives there now, and it provides half of the world's oxygen. It's something that when we describe the blue marble, our planet, the ocean, that's almost the most important thing. So we wash with it, we drink it, we eat it. You are 2/3 water. But have you ever wondered what that water does inside your cells? What it is about it that you need so badly? Well, let me tell you a little bit about what water does inside you, why you get thirsty, why it is that all of life on Earth needs this substance. Inside your cells, inside every one of your cells, there's water. In between your cells, there's water. Water is the substance that lets your cell membranes into the right shape. Inside your cells, the proteins and the DNA, they don't function if water isn't present. The molecule makes those other big, complex things of life, they make them function properly. When a protein is made inside your cell, it's constructed as a chain of amino acids, a complex set of molecules. It's a big, long, floppy line. But no protein functions like that. No protein will ever work if it's just a line. But if evolution's been a remarkable thing, because these proteins that we make, some parts of them like water, some parts of them don't like water, and when you make that protein and shove it into the middle of a cell, it automatically folds itself up into a three-dimensional shape where the parts that do like water are on the outside, the parts that don't like water are on the inside, creating the perfect shape. And then that protein can go on and do whatever it needs to do, whether it's build something inside your body or send a message or whatever else. Water also transmits electrical energy from outside to inside cells. It powers what's going on inside there. These are just a few of the things that it's doing inside you. That's why you need to drink water. And that's why all life needs water. In fact, all of life on Earth uses water. Wherever there is water, there is life. And wherever there isn't water, we've not found any life at all. Humans, I think, have always known that water is somehow special. Even if they don't understand the chemistry or the biology that we understand today, and I've just sort of hinted at, we've always known that there's something special about it. In myths and legends from the first human beings, water always plays some sort of role. If you think back to ancient flood myths, or the fact that water is used as a cleansing in many rituals, even in the Bible, in Genesis, God moves over the still waters to create the heaven and the earth. Every religion, every myth, every culture has something about water that they knew was special, they venerated in some way. We venerate it in different ways now, whether it's alongside those myths or whether it's with science or whatever else. We still know it's important. But what I like about those myths, what I like about those legends, what I really love about them is that they contain a kernel of truth. They all talk about water being celestial and heavenly. And in fact, it absolutely is celestial and heavenly. It really did. All of our water on the surface of this planet, all the water inside you, it came from space. And to understand how all that came from space, let's just go back to the beginning of the universe, just a casual sort of saunter back to that 13.7 billion years ago, when the Big Bang happened. The Big Bang happens, and for a few minutes, because it's so hot, there's nothing that can actually coalesce out of that. It's just energy, it's pure fiery energy. 3 minutes later, things have cooled down slightly, it's expanded, and all the hydrogen atoms that will ever exist, all the hydrogen atoms in the universe are created in that first 3 minutes. And they still exist today, all of them. And of course, and I don't have to tell you, the chemical symbol for water, H2O, 2 hydrogen atoms, 1 oxygen atom, probably the only chemical symbol that's part of English vernacular, pretty much, I would say, or any vernacular. H2O, so you've got the hydrogen. So where does the oxygen come from? Well, the hydrogen, as it sort of expands through the universe, it doesn't expand in a completely uniform way. It expands in clumps. And wherever there's a clump or a cloud of hydrogen that's a little bit close together, the gravity brings it all together, and in the center of those clouds, the hydrogen starts to fuse into helium and other elements, releases some energy, and that's what the first generation of stars is. And the star essentially is fusing hydrogen, burning. Over few hundred million years, as the star runs out of fuel, all of the hydrogen in the center is eventually burned away, or fused away, the star doesn't have anywhere to go, and it explodes. And these explosions are some of the most beautiful objects in space. So you've seen pictures of things like this. This is the Helix Nebula. And the Helix Nebula it's about 700 light years away, and it's a few light years across. The size of this thing is incredible. It's absolutely enormous. Our solar system is a few light hours across. This is about 4 or 5 light years across. And what you're seeing there is not real colors. They're false colors taken by probably the Hubble Space Telescope in this case. And what you're seeing is the distribution of elements. So these elements like carbon and oxygen and nitrogen are created in the centers of these stars that I told you about, and then they're thrown into space as detritus, as dust, as basically leftover material as the star dies. And in there's lots of oxygen. And it's in here that you get the water that we know of forming. So in a planetary nebula like this one, or perhaps even like this one, the Eagle Nebula, which is one of the more famous ones, it's 7,000 light years away and about 4 or 5 light years across. It's rich, filled with dust and gas. And within there's still lots of hydrogen. So new stars will form. New stars will form with that hydrogen. And around them, there's lots of rich material for planets to form. And I mentioned that in there's carbon, tiny, tiny, tiny grains of carbon, dust essentially, 1,000th the width of a human hair. And on these tiny grains of carbon, you get oxygen atoms and hydrogen atoms bumping into them in the vacuum of space. Occasionally, both of them will bump into it at the same time. When that happens, you get a molecule of water. And over hundreds of thousands of years, each of these tiny grains develops a sort of film of ice, and these things will float through space and eventually come together as stones. The stones come together as rocks. The rocks come together as boulders. The boulders form the planets. And in a planetary nebula, when our star was forming 4.5 billion years ago, this is what happened. And our planets formed, our inner planets at least, formed in this way. The Earth, if you went back 4.5 billion years ago, would be pretty unrecognizable. On the surface, there was water, but it was rapidly evaporating away because the surface was so hot. There was so much volcanic activity. And if you go back to a certain period of time, you see it's just a dry rock. We clearly have oceans, though. So where did they come from? Well, not all of those tiny grains of carbon, not all of those tiny rocks ended up forming planets. A lot of them just ended up being chucked out the edge of the solar system. And they still exist there today. But about 4 billion years ago, something disturbed those rocks, disturbed those dust grains. And huge numbers of them, like billions of them, over the course of 500 million years, rained down on the Earth. It's a period of time that geologists call the late heavy bombardment. And for 500 million years, the Earth was bombarded by tiny asteroids and comets, each of which had a tiny amount of water created in space, like I said. And they brought our oceans to our planet. Every single molecule of water inside you, every single molecule of water on the surface of our planet came from the edge of our solar system. And it's actually younger than the rest of the planet. So today we have 1.5 billion cubic kilometers of water on the surface of the planet. Most of it, though, is salty. It's in the oceans, so it's completely inaccessible to us. We don't really do anything with it. And of the remaining 3% or so, which is fresh water, 2 of those percentage points is frozen in ice caps, and less than 1%, therefore, of the entire volume of water of the Earth. That's a tiny, tiny, tiny amount. Less than 1% actually is available for all of life on Earth to share and to build everything that actually we do with it. To give you some context, here's the Earth, with all its water removed. If you were to take all of the water on the surface of the Earth and put it into a ball, this is how big the ball would be. All of the surface of water. And that ball is 800 miles in diameter. It's all of the water on the Earth, everything. And if you want to know how much fresh water there is, there's the fresh water in the corner. Can you see that? That's probably a few hundred miles across. And you probably can't see it on this diagram, so I'll blow it up slightly. There, just on the bottom right, that 40 miles across ball is the water accessible to all of life on Earth for the past 3.5 billion years, which has been recycled again and again and again and again. And it's not a huge amount at all. We share that with every plant, every animal, everything. Now, humans, as I said, have always venerated water and known that it was something important to them. But for most of our history as a species, we've kind of gone wherever the rains have gone. We've depended on, as hunter-gatherers, we've moved around to wherever the waters were. But about 12,000 years ago, when agriculture started to become developed, we started to move water around ourselves and collect it and dig irrigation channels. We wanted to build civilizations. And so cities and empires since then have been built on diverting rivers and moving water over huge distances. The Roman aqueducts, which are some of the most famous bits of engineering, a few thousand years ago, they would move millions of gallons of water to satisfy the needs of what was then the biggest city in the world, 500,000 people in ancient Rome. Around the same time, in what was ancient Egypt, in Alexandria sat above storage tanks, which were constantly refilled by the Nile. And the Nile itself, which is one of the most important rivers in the world and is an important source of political power. Back in Alexandria's time, it was supplying that particular city. And when these sorts of things were being built there and in other parts of the world, they weren't concerned too much about, let's say, efficiency or how much water they were using. They just wanted to get water from one place to another to allow their cities to be built. And if a city didn't have access to water, it was quickly abandoned or didn't survive for very long. And it was perhaps fine 6,000 years ago when people started doing these things, 7,000 years ago, when only 1 million people lived on the Earth. So 6,000 BC, the population of the Earth was about 1 million people. There's still plenty of water. I'm keeping this picture up only just so you can keep reminding yourself how little water there actually is. But that was plenty for those 1 million people. Today, there are 7 billion of us, and we haven't created any more water to use, or there's no more. It's just the same amount. And of course, the amount of agricultural land that we have now is much, much bigger. From 1900 to 1950, the amount of agricultural land actually doubled, and it doubled again from 1950 to 1990, and it's still growing. More than half of the world's population lives in cities, and cities require huge amounts of water to keep running. We've built canals and lakes and all sorts of artificial things underground. We don't really see the water that we bring to our cities these days. And as we become more industrialized, we need water for goods. We need water to produce electricity. Water doesn't just flow around us and annoy us when it rains from the skies, but it's actually a part of everything that we touch, taste, and see. It flows through all of it. I mentioned that you've interacted with water today. So you might have had a shower, you might have drunk water, you might have had food, But most of the water you're going to use today or have used today, you're never going to see. You don't touch it. You don't even come anywhere near it. A kilogram of beef, let's say. So you've had not that you're going to personally have a kilogram of beef, but a kilogram of beef takes 16,000 litres of water to make, because it takes that much water to water the plants and to then distribute and grow the cows and so on. A cup of tea, the water footprint of that is 35 litres. A sheet of paper is 10 litres. A microchip is 30. Don't worry, I'm not going to start listing loads more numbers, but a kilogram of cotton, that's my last one, 10,000 litres of water on average. In some places, parts of the world, it's even more than that. Around 70% of the water, fresh water on the earth, is used for agriculture in some form, whether it's growing wheat or maize or rice, or whether it's food for us or livestock. A large part of the rest is used to generate power or for industry, to make goods, to transfer things. And most of that water use happens in the richer nations, as you might expect. Americans use about 600 litres of water a day on average. Europeans and actually Australians as well, about 250-ish litres of water a day. Compare that to the billion people living in many parts of the developing world who use about 19 litres of water, and double that population that don't actually have access to basic sanitation. And you can already start to see then, given that if places like China and India, as their populations increase, as their populations want to have a better standard of living, they want to eat more protein-rich diets, they will need much, much more water to supply that standard of living. They were going to need more power, more water for their power sectors too. So there's going to be a need for even more water than we've seen already. And as there's another thing that will stress everyone else, which is that as temperatures rise around the world because of climate change, it'll wreak havoc on agricultural lands. It'll force certain parts of the world to have too much water and certain parts of the world to not have enough water, which means people have to move. People cannot live if they can't grow crops in their area. There are already examples of situations where drought is causing very localized problems. Last year, a heat wave in India caused the deaths of several thousand people, and water shortages there exacerbated those problems. In the Brazilian city of Sao Paulo last year, there was a drought, which is home to about 20 million people. There was a drought that led to people there in what is traditionally known as the city of drizzle. The drought got so bad that residents began drilling through their basements and through the ground in car parks to try and reach groundwater. These are sort of individual, small-scale examples of things that are going to increase as people realize that the water that they've had so easily accessible, the water we don't even think about how it gets here, that stuff will become much, much more complicated and difficult to get hold of. In 2002, NASA sent up a pair of satellites to measure the gravity field of the Earth. Now, why do they want to do that? Well, actually, that's a very good way of looking at how water moves around the surface of the Earth. By looking at the changes in the gravity field, you can look at how water moves. And what they found was that in the years between 2003 and 2010, in some parts of the Middle East, around the Euphrates River, for example, 144 cubic kilometers of fresh water, which is about the volume of the Dead Sea, it disappeared. Most of it disappeared because it was drilled out of the ground in groundwater. There are aquifers there, there's groundwater there, stuff that's been sitting there for a long time, which is the backup, if you like, of any sort of region. Normally, if you think about rains coming from surface water, then these things are recyclable. But groundwater, aquifers, are things that have been there for a very, very long time. They don't get replenished so easily. They were being drilled into because of droughts in those areas. And a huge amount had completely disappeared and become unavailable. Farmers were facing droughts, so they pumped out the groundwater. The Iraqi government actually drilled nearly 1,000 wells to try and exacerbate the problem. These are short-term solutions which have very, very long-term impacts. And using the data from the GRACE satellites, NASA has concluded that the amount of desperate water withdrawal from these aquifers because of the amount of people, the amount of drought, the weather patterns changing, they've said that 13 of the 37 largest aquifer systems in the world, and there are only 37, 13 of them, 1/3 of them, are becoming so rapidly depleted that there's no possible way that they can get recharged in any sort of human timescale. And this is a problem. This is the stuff of tension. This is the stuff where if they run out, if they're the kinds of things that disappear, then we've got nothing left. So you can't magic up water from nowhere. You have to essentially move your people. You have to move. People will argue about access to water, and they do, and they have done for thousands of years. Take the Middle East, which is some of the places where humankind has been for the longest, but also they've argued for the longest about war. There are many ideological, religious, geographical, political disputes in this part of the world. It's a part of the world that's incredibly arid, and every major river here crosses international boundaries. And even as far back as the 7th century BC, there were Assyrian kings who would try and divert rivers to seize control of different parts of Arabia. In more modern times, control of the Jordan River and the Jordan River basin has been at the root of conflicts since the 1940s. The Jordan itself is a relatively small river, but it's shared by many, many nations that will often fight with each other. Jordan, Syria, Israel, Lebanon. And because of those the volatile politics and the volatile military dynamics, and there's no other source of water, you can see there that water becomes the contributing factor to a lot of problems. One of the academics will tell you that the 1967 war was essentially started, or a large part of it was caused by the Arab League trying to divert the headwaters of the Jordan away from Israel. And of course, a country that in that part of the world that doesn't have any access to water, a country like that will die. Now, today, water stress by itself is unlikely to be the cause of a government falling, but it's definitely going to be something that threatens food production. It threatens energy supply, and it will put stress on places and governments that already have social tensions. US intelligence agencies are obsessed with water, and they point to places where they think that tensions might arise which might cause the US and all of us problems. So they point to the Nile, the Tigris, Euphrates, the Mekong, the Jordan River, the Indus, the Brahmaputra over towards India. Here, they say, water shortages could risk instability and state failure and increase regional tensions. One example of that was, in the recent years, Ethiopia has wanted to build an enormous dam, the Renaissance Dam, on a tributary of the Nile, to essentially give itself power, electricity, but also to provide its farmers with agriculture. Egypt, of course, is not happy about this because it controls the Nile, it thinks. And traditionally, in the accords signed in the 1920s, when the British left, Egypt has control of this river. For a long time, they argued, and Egypt even unofficially talked about military intervention of some sort, which is a terrifying idea. The Ethiopians wouldn't back down. But cooler heads did prevail last year when Ethiopia, Egypt, and Sudan signed a deal to make sure that the Renaissance Dam wouldn't affect, or at least they said, wouldn't affect the flow of water through Egypt. Now, that's something that is yet to remain to be seen when it's built. In any case, military conflict is not something that in modern times you see as a result of water stress. And even if that was the case, it seems like there are probably mechanisms we'd use to get around it. If two countries are about to go to war, there are institutions set up specifically to stop them doing these sorts of things, international institutions, the UN, etc. Whereas most people who worry about conflicts over water worry about them happening within countries. So with, for example, businesses versus their citizens, or governments versus their citizens in some way, or citizens versus each other. Acts of terror might happen as a result. And there's a lot less international governments and so on and groups can do to actually deal with those sorts of tensions. By the middle of this century, the United Nations has predicted that 4 billion people will live in situations where there's water stress, by which means they don't have enough water for not only their daily bathing and eating purposes, but also to make their goods, provide their electricity. 4 billion people. And if you think the predictions for population around that sort of time are around the 8-9 billion around the world. And climate models also show that as global temperatures rise, extreme droughts will increase in parts of the tropics. It will lead to failed crops. Almost a third of the current agricultural land in the world will be at risk by the end of this century. There are going to be mass migrations of people. They are going to go where the food is. Even before the movement of Syrian refugees in the last few years, the European Union, the European Commission, scientists in those places were already engaged in considering what's going to happen as a result of climate change in terms of movement of people. They're expecting lots and lots of people from the southern Mediterranean, the northern Africa, to move upwards into Europe as a result of climate change, as a result of environmental degradation in their parts of the world and lack of water. The wet areas of the world are getting wetter, high latitudes like the Arctic and some parts of the tropics. The middle latitudes, the semi-arid areas, the places we already know that are stressed, are going to get even drier. The Middle East, North Africa, South Asia, they're all projected to experience huge water shortages over the coming years, not only because of climate change, but because of decades of bad management and overuse. Now, we've used water to build our world and not really thought much about how we waste it or where the resource comes from. But remember, that resource is not increasing, it's not changing in any way whatsoever. It's only getting more and more restricted as we pollute parts of it and put it out of circulation, in fact. We've used it unthinkingly for the entire history of human civilization. And mostly until now, we seem to have got away with it. We're now racing dangerously, I think, towards the end of that complete water-rich era. Thanks very much.
This session was recorded live at the Sydney Opera House and presented by the Sydney Opera House and the Ethics Centre. The Ethics Centre delivers programs and experiences designed to bring ethics to the centre of our life. We offer free counselling for individuals, consulting, leadership and development services. As a non-profit charity, we rely heavily on donations to continue our work, which can be made via our website.